Alright, in this video we're going to talk about two of the other things that will affect the acidity of organic molecules. And the last video we went through three characteristics of the atom directly attached to hydrogen that will affect the acidity of that hydrogen. But there's also more remote effects. There are atoms in other parts of the molecule or the overall molecular structure will also affect the acidity of the molecule. One of the very common effects is called the inductive effect, and inductive is just a word derived from induce, or to cause. And so what I like to do again is to memorize structures of molecules and the pKa's of those molecules so I can get an idea of how the structure affects the pKa. So methane, CH4, has a pKa of about 50, which makes it one of the very least acidic compounds we're going to study, and that's often a benchmark for acidity or lack thereof. Is methane is very simple structure, simple bonding, and has a pKa of 50. Trifluoromethane has a pKa estimated to be between 27 and 29 depending on who you talk to. So the presence of these fluorines, which are not directly attached to that hydrogen, are going to affect the pKa and the acidity of the molecule of this acidic hydrogen. So in each case there's a CH bond where the hydrogen is the most acidic atom in the molecule, and the other atoms in the molecule are going to affect its acidity. So the fluorine is going to pull electron density away from the CH bond inductively, and so it's what I would call the inductive effect is sort of a remote electronegativity effect. So we talked about electronegativity of the atom directly attached to hydrogen increasing its acidity. Now we have an electronegative atom farther away from the hydrogen, but still having an effect. And so acetic acid, ethanoic acid, very common acid that we're going to have, so CH3COOH, and we can look at its structure, and that's got a pKa of about 5, right, to round it to whole number, 4.74 if you want a more exact number. Trifluoroacetic acid has 3 fluorines in the place of some of the hydrogens, the non-acidic hydrogens, and these fluorines are going to again pull electron density away from the rest of the molecule because fluorine's so electronegative, and that's going to reduce the pKa or increase the acidity. So the pKa value of trifluoroacetic acid is 0, and it makes it a very strong acid. So the presence of more electronegative atoms in a molecule is going to help pull the electron density away from the hydrogen, making the hydrogen more positive and more acidic. And so looking at these, you can see that 3 fluorines, 2 bonds away from the acidic hydrogen, is going to drop the pKa from 50 down to about 30, so a big 20 pKa unit jump. In the case where the hydrogen is bonded to an oxygen, which is bonded to a carbon, which is bonded to another carbon, which is bonded to the fluorines, now we have 3 fluorines about 5 bonds away from this hydrogen. They're going to have a much lower effect, because a much smaller effect, because they're much farther away. But again, the presence of the electronegative elements in the compound is going to generally increase the acidity, and how close those fluorines are to the acidic hydrogen is going to affect how much of an effect it's going to be. So the more electronegative atoms in the molecule draw electron density away from the other atoms in the molecule, especially the atom attached to hydrogen, and that will, as they say, stabilize the conjugate base. So let me draw the structures of these guys I've been comparing. Carbon attached to hydrogen with 3 other hydrogens is methane, which has a pK equals about 50. And if you put fluorines in there, now these fluorines are going to remove the electron density, pull it away from the carbon, making the carbon more electropositive, and that's going to allow it to grab this shared pair of electrons a little better, releasing the H plus a little more. In the language of the last slide, it said that the conjugate base is stabilized, and the conjugate base here is a very unstable carbanion, right? So this negative charge makes this very reactive, but the fluorines pulling electrons towards itself is going to essentially remove some of the negative charge from this lone pair and distribute it elsewhere in the molecule, making this a little less potent of a negative charge and a little less likely to grab that H+. So stabilization of the negative charge by sort of removing it out to the fluorines, which all, because of their electronegativity, take on a slightly negative charge themselves. That's going to take the negative charge away from the rest of the molecule, thereby stabilizing the negative charge on the lone pair. So this guy, pKa about 27 to 29, is much more acidic due to the presence of those fluorines. And again, the other molecule that I talked about, and this one is going to have a combination of inductive and resonance effects. So we'll talk about acetic acid and why this OH bond has such an acidic hydrogen on there with a pK equals 5 due to the resonance, which also stabilizes the conjugate base. But that compared to if you put some fluorines in the molecule, then these fluorines are going to draw electron density away from the carbon, which then is going to in turn draw some away from the other carbon. And you'll notice this is a much less of an effect because this fluorine, its pull is not going to be felt so great 1, 2, 3, 4 bonds away from this hydrogen, but it still is overall going to move electron density away from this hydrogen, making it more delta positive or more acidic. So this guy, pKa equals 0, and even if the explanation sounds a little hand-wavy, the presence of electronegative elements somewhere in the molecule does make the molecule more acidic. It's not as dramatic an effect as when we compared the atom attached to hydrogen being more or less acidic, right? So that was what some people would call the element effect, but the electronegativity of the atom directly attached to hydrogen is a very major effect, but that's when I would say it's an electronegativity effect. They use the term inductive effect when the electronegative element is acting from a distance from the acidic hydrogen. So I would call it a remote electronegativity effect, but I'm not in the business of reinventing terminology for the organic chemist. So we'll still call it an inductive effect, although in my mind I consider it to be a remote electronegativity effect, increasing the acidity of the hydrogen in the molecule. The other one that I wanted to talk about briefly, because it's again a fairly short discussion in some sense, is hydroxide, OH minus, right, water, H2O, and hydronium, H3O plus, have dramatically different acidities, right? And each one, the hydrogen, is directly attached to an sp3 oxygen. So in terms of the environment of the hydrogen is directly attached to an sp3 oxygen in all three cases. So you might argue that the pKs are fairly similar, but here the pK is 42 again estimated. pKa for water is about 16, and the pKa for the hydronium, I believe, is about minus 1.7. And you might want to fact check all of this, because I'm remembering from memory from at least a year ago, the last time I looked these up, but I think that's, at least the trend I know is pretty accurate, that the positively charged version of this is going to be much, much more acidic than the neutral, and that's going to be much more acidic than the negative. And that should make sense, because pulling a hydrogen away from something that's already negative is going to be quite a chore, whereas pulling a hydrogen ion, an H+, away from something that's positive to leave a neutral, stable water molecule should be a relatively easy task. So some people will call this the degree of protonation, that there's 3 H+ on this oxygen, 2 H+ on this oxygen, and 1 H+ on this oxide, right? So they would say that the greater the degree of protonation, the more acidic and the lower the pKa. I just simply am going to go with charge, that the positive molecule or ion, positive ion, is going to be more acidic than the neutral molecule, which in turn is going to be more acidic than the anion. And again, the rest of the factors that you would consider, the hydrogen is attached to an sp3 oxygen in all 3 cases, mean that the other factors we've talked about are equivalent for all these, except the charge. So charge is often not on the lists of factors that affect acidity, but as you can see, it has an extremely important role in defining the acidity of different things. Cations are generally much more acidic than neutrals, and neutrals are much more acidic than anions. Anions tend to be bases rather than acids. So inductive effects and charge are very important if you want to understand the acidity of different compounds and ions. And hopefully this video helped to increase your understanding, and certainly would give you some specific examples to think through as you're trying to sort through for yourself what affects acidity.